Okay, welcome everyone. Mike couldn't make it here, so I will do the mic for today. So first of all, are there any visitors for this week who want to introduce themselves?
Yeah. Hi, I'm Claudio. I am from Berkeley. I'm postdoc there in particle pheno, and I'll be here the whole week. Nice to be here.
What office are you in?
Sorry?
What office are you in? You're
912, right?
912,
okay,
yes, that's
good.
right.
Are there any other visitors? Okay, if not, then we are happy to have Cameron Norton today, who's a PhD student at CCPP, and she'll tell us about primordial black holes.
Hi, I'm Cami Norton. I'm a third-year graduate student, and I'm working with Matt Cleveland. And today I'm going to be talking about a project that we did on a mechanism for generating primordial black holes that could account for all the dark matter in the universe. So as everybody knows, 25% of the universe of the energy density of the universe is in the form of dark matter, but its origin and nature are still very much a mystery. And there's been decades of searches for a weakly interacting massive particle, but no conclusive signal has been found. Another alternative is that instead of being in the form of a particle, the dark matter is in the form of little tiny primordial black holes. So first I'm going to talk about primordial black holes as dark matter more generally. I'm going to talk about the currently allowed mass range and properties of black holes that have that mass range. And I'm going to talk about where the constraints are coming from that give us that mass range, and then where constraints might come from in the future to help narrow it down. Then I'm going to talk about a mechanism for producing primordial black holes with the correct mass. And in this mechanism, bubbles nucleate during inflation, they grow, and then they collapse and form black holes. So first I'm going to talk about the way that the black holes form during this process, and then I'm going to get into a bit more technical parts where I talk about the details of the tunneling, which corresponds to the bubble nucleation, and that will let us get information on what the resulting mass spectrum is. Okay. So first, mass range properties. So the allowed mass range for a monochromatic spectrum of primordial black holes, which means a spectrum of black holes where they all have roughly the same mass, is 10 to the 17 grams to 10 to the 23 grams. This is called the asteroid range. The Schwarzschild radius of black holes that have this mass is for a black hole at the middle of this mass range, like 10 to the 20 grams, it's 10 to the minus 10 meters. Which is about the radius of a hydrogen atom. So if these black holes are accounting for all of dark matter, there's a bunch of little tiny hydrogen atom-sized black holes floating around the universe.
And is the low mass cutoff set by the evaporation timescale?
I'm gonna get to that.
Does this assume some distribution of the black holes?
What?
Does this assume some distribution of the black holes in the universe?
Oh, yeah, I mean, so they're assuming that the distribution is like spiked, so it's just one, it's all the black holes having the same mass.
Or distribution in space, like
Oh,
yeah.
yeah, I mean, it would be distributed just like dark matter is distributed now. Okay, something else you might want to know is what are the chances that one passes through Earth? And the number passing through Earth is 5 times 10 to the minus 19 inverse seconds. So that is about 10 to the 18 seconds for one to hit the actual Earth, so it's not very likely. But this is for the middle of the mass range. For one of the black holes at the lower end of the mass range, like 10 to the 17, then the time to hit the Earth is more like 10 to the 15 seconds. The age of the universe is 10 to the 17 seconds. So if it's at the lower mass range, then there's a chance that it, like on the order of 100, could have passed through the Earth.
But there's basically no observable consequences of that anyway, right? If a black hole of that mass passes through the Earth, nobody notices, right?
Well, if it passes through you, you die.
Is that true? I'm not sure that's true, right? Because gravity is very weak, and and the Bondi rate would be extremely low in terms of accretion.
If it's like, we calculated it, if it's like, I think it was a couple meters, and then it has the same acceleration as the acceleration due to the Earth.
I mean, if you get hit by an asteroid, it hurts because of the Fermi pressure.
I mean, they're
Not
also
because of
super
gravitation.
hot.
Asteroid with a hydrogen atom, it's like what's the roche radius of human? Would that rip you apart? Right?
I don't think
I'm
so.
pretty sure it's also extremely hot.
Anyway, we should work out what the consequences are. I thought I figured out earlier that the consequences would be minimal.
Well, that's like.
Yeah, if it's close to you, then
Yeah.
your acceleration due to the black hole is stronger than your acceleration due to gravity of the Earth.
And you said that's like when it's like a meter or two away?
Yeah.
You guys are like, whoa, that felt weird.
Yeah,
I don't
but
think it takes
imagine
any
if
of
it
you
passes through you.
Random levitation events.
Exactly, it happens all the time.
It's also moving at 200 kilometers a second, so.
So it's not around it.
Okay, speaking of ways to die, the temperature, the temperature scales is 1 over the mass, and for this range, it goes from 10 to the 3 Kelvin to 10 to the 9 Kelvin. A light bulb has about 2,000 to 7,000 Kelvin. So that's within this range, so they're actually emitting light that we would be able to see. So if this is dark matter, then the name dark matter is kind of a bit of a misnomer because they're not actually dark. They're really bright.
Sorry, this is a silly question. Did that affect how good of a candidate this is for dark matter then?
Well, they're really rare and really small, so you wouldn't see it unless.
Are they really bright though? Like the luminosity may be low.
The luminosity is like 5 times 10 to the minus 2 watts. Which is visible.
That's watts in
So this may be a really naive question, but if it's visible, has anyone tried just looking for it?
It's not visible, like, I mean, it would be visible if one was close to you on the Earth.
Okay.
But it's not like, it's visible in the sense that it doesn't, like, usually when we think of dark matter, we think of that it's like not interacting with light, or like there's no chance that you could see it. But this one, it's like, it's dark in the sense that we wouldn't see it, but it's not like theoretically if one passed you, there's no reason you couldn't see it.
Okay, so it's just because it's so rare.
Yeah, it's rare and tiny, so like you can't see it from far away.
But you could turn that into an intensity on the sky.
Yeah.
There would be there's a background intensity on the sky, and we do have some limits on the background intensity. I'm still guessing it's going to be too low to be observable. it takes a real, you have to do an integration.
I mean, a light bulb scale thing passing through the Earth once every like 100 times in the history of the universe is like probably pretty sparse.
No, but I'm thinking about just the intensity that
Sure,
the
we just stare at the galactic center.
universe has a lot of volume.
Yeah, I didn't calculate that, but I mean,
I think it would still be very small.
I think the people
Probably.
like Carr would have probably calculated that by now.
Yeah, it must be.
I think it's tiny.
It probably.
Okay, so now I'll talk about the constraints. From the lower bound, the constraint arises from Hawking evaporation. So black holes that are less than like 5 times 10 to the 14 have already evaporated. Then black holes in the range from like 10 to the 15 grams to 10 to the 17 grams are basically emitting radiation that we would be able to see. They're producing gamma rays and electron-positron pairs. And this would be, this is constrained by measurements of the galactic and the extragalactic gamma ray background and Voyager 1. The upper bound is that.
So basically this 10 to 17 grams, that's exactly from the bound. You don't see
Exactly,
them, right?
exactly. And it
Yeah.
helps that you get gamma rays because the bounds are stronger.
Yeah, exactly. So the upper bound is set by microlensing and of stars in M31. It's measured by the HFC. It's difficult to push this lower just because of how small the black holes are. They get small relative to the optical wavelength. And then there's like finite source effects coming from the stars. But a possible future constraint is dynamical capture by stars. So if we have a star and a primordial black hole passes through it, it's going to heat up due to gravitational friction, and then there's a chance for it to get in a bound orbit with the star and eventually settle into the center. And once it settles in, it can accrete a lot of matter, and it can grow enough to strongly affect the stellar evolution. So then there's 2 possible constraints that can arise from this. One is like stellar survival, so just the fact that we see a lot of stars that haven't died by this. It turns out that this doesn't add any interesting constraint because they're just too rare. But observations of stellar destructions is a more promising avenue for future constraints. Because the stellar destruction events, I think were, it was like a rate at 3 to 4 times less than the rate of supernovas, so like we would see them. But more modeling is needed to better understand the evolution of the star once the primordial black hole gets inside of it.
Do you know if anybody has thought about just the forward scattering problem? Like, you have a black hole, there's small deviations of photons. It's like microlensing, except just thinking of the scattering. So seeing like a scattering halo around distant sources or anything. Has anybody thought, have you seen a calculation like that?
I
I feel like there's something that could be calculated.
I haven't seen it.
I haven't either, I have to say. I was searching and I couldn't find it.
For a while, people thought that the mass range was kind of ruled out to a certain extent for being all of dark matter because there was some analysis done with white dwarfs. But then more recently, a more careful analysis was done, and at first they thought that the primordial black holes would blow up the white dwarfs, and then the new analysis showed that it wouldn't. So there's no constraints coming from that anymore.
Also from lensing, right? People thought that lensing ruled it out
Yeah.
because it didn't take into account planet size effects.
Mm.
Which is, well,
Okay, so now I'm gonna transition from talking about primordial black holes as dark matter in general to the particular mechanism that we study. And this mechanism is collapse of vacuum bubbles. So once we have this mass range where we know that it's possible for primordial black holes to account for all of dark matter, the challenge is coming up with a mechanism that's going to produce them with the correct abundance and the correct mass distribution that they can fit with the constraints. So one way of doing this is that people think of a lot is large density fluctuations, but this tends to have a really wide mass range. It does not end up being monochromatic. Another way of creating black holes is that something happens during inflation that creates some sort of an object, and that object later turns into a black hole. And if the thing that happens during inflation only happens during a very small period of time, then the black holes will all end up having a pretty definite mass.
Question?
Yeah.
Is there a reason why we want a monochromatic spectrum? Like, I thought having a more diffuse spectrum means you can avoid constraints more easily.
As far as I know, a lot of the constraints are done assuming a monochromatic mass spectrum because it's just easier to, like, a lot of it is simpler to do it that way. A lot of times, like, the challenge is that a lot of mechanisms don't produce a monochromatic mass spectrum.
Right.
But it fits nicely into the constraints. Having it fits well.
So I guess the question is, in what sense is it a challenge?
In what sense is it a challenge to create a monochromatic mass spectrum?
No, why?
Or why would you want one?
Yeah. So.
I think, my impression is that it fits better into the constraints than a and it's also than a wider mass distribution, and also it's nice in the sense that, like, we know the constraints a lot better for a monochromatic mass spectrum than we would for a wider one.
Yeah, I mean, if it's in that range, it's not ruled out. If it's outside that range, it might be, depending on what it is.
But this range is only for monochromatic.
Yeah, but I think if you had a broad spectrum in that range, you'd be fine, because then in every mass range you'd be fine.
Okay, so we're studying nucleation of vacuum bubbles, and this was first studied by Blanken, Garriga, and Zhang. So one kind of object that can be created during inflation is a vacuum bubble, and it's just a bubble of a different energy density than the ambient phase, which in this case is inflation. So I'm going to talk a bit more about the formation and nucleation of the vacuum bubbles in the next part. But for now, just basically during inflation, there's the probability that you can tunnel into a lower energy density state and create a vacuum with that energy density. Now, because the bubble's energy density is less than the energy density of inflation, the bubble is going to expand outward because there's pressure. And then it will reach horizon size. And once it reaches the size of the horizon, then it gets caught in the Hubble flow and it expands with the expansion with inflation, which is exponential. This is the Hubble during inflation. So the bubble expands exponentially with inflation, and it has a radius that is at the end of inflation that is exponentially dependent on when during inflation it formed. Tn here is the nucleation time. And sometimes this is also called and the number of E folds from the end of inflation that the bubble nucleated. But the point is just that the size of the bubble is exponentially dependent on its nucleation time and nothing else. Okay, so during inflation, the universe is expanding faster than the horizon, so once the bubble leaves its horizon, there's no chance for it to come back inside of it. Then we move to radiation domination. In this case, the energy density is less in the ambient space than it is in the bubble. So at first we have the bubble expanding really rapidly. It comes at rest with respect to the Hubble flow because of the pressure of the radiation. And then once it's at rest with respect to the Hubble flow, it can come within its horizon because during radiation domination, the universe is only expanding as square root of t instead of exponentially, so the horizon is growing faster than the universe. So then the bubble comes into its horizon and collapses. And it forms a black hole with a mass that can be approximated by the time of its Hubble crossing over g. And then we can solve for the Hubble time in terms of the nucleation time, and we get that the mass is (1/ghi) exponential of 2 times the number of E folds from the end of black hole, from the end of inflation that the black hole nucleated. So here we have that the mass is exponentially dependent on the time of the nucleation, and that's all. So
Question.
Yeah.
Can you perhaps explain, going back to why the bubble expands? Because of the density inside is higher and is lower. Often I would expect if the density inside is less, then it would collapse. Because the density outside is higher, it would squeeze it in.
Well, I think it's an energetically preferred state, so it would stand.
I can see that it is energetically preferred, but the energy outside exists. This is my understanding, that the energy outside exists, and the energy outside that exists would like to occupy as little space as possible, so I would expect it to collapse the bubble.
It's inflationary forces fighting against that, right?
What?
The story here is that that is fighting against inflationary forces, right?
No, at first it's like the bubble is much smaller than the Hubble radius. So at first you do need the pressure to be able to expand it, and then once it gets to the horizon size, it gets caught in the Hubble flow. But before that,
Generally, forces and pressures are gradients of energy densities. So if you have a situation like this, you expect the pressure to go the other way. You probably have in mind some gas or something.
Yeah.
That's a different situation.
Okay.
Dark energy, it's relativistic.
Okay.
Yeah.
Thanks.
Yeah.
But by the way, there is an assumption, right? You've assumed that the I part of the universe collapses to radiation and standard model particles, which obviously does, because check us out. But the B part of it has not gone through a similar transition. The assumption is that inside the bubble, it doesn't go through a similar transition into standard model particles.
right?
So it's like there's some, because in principle, in that vacuum, maybe you go to standard model particles earlier, and then there would be a different story.
I think when I draw the potential in the next part, that will make sense.
Okay, good.
It's related probably to this question. So what is exactly the condition when these bubbles turn into a black hole? Because quite often bubbles don't turn into black holes, right? When you have some phase transition.
Well, once the bubble comes within its horizon, my understanding is that it's like, it's this really heavy, over-dense area of space, and it has to collapse into a black hole.
Well, but I can ask him, what is the condition for it to come within its horizon?
Oh, the condition for it to come within its horizon is just like you set the. I mean, we're just we're just assuming that it's expanding with like radiation, so it's like you're just set like it's when the scale factor. It's like it's when the radius is equal to the radius of the Hubble.
I think maybe Sergey's asking about the assumption rho r is less than rho b.
Oh, this?
Yeah, it should be somehow. So what is rho b? Ah, that's the energy density.
Yeah.
So like our universe has gone into this power law behavior, but the bubble is still in the exponential behavior, so our universe gets less tense.
Oh, is it the stories like the relative energy density inside and outside flips once we move into radiation domination?
Yeah.
And so the pressure story you were telling before flips and that. Okay.
Right.
And so basically the assumption is that radiation is present only outside the bubble, but it doesn't enter inside the bubble. So
I think it's just there's lower energy density outside the bubble, so the pressure story we were talking about before flips, and the pressure density becomes like a force that will tend to push the bubble, to squeeze the bubble rather than having it expand.
It's a little bit more complicated, but like, yeah, that's how we roughly, like, we're trying to get order of magnitude estimates for these. I mean, there is like a shock wave that happens when the radiation runs into the bubble, which changes the resulting mass a little, but.
The basic assumption is just that the energy density in the bubble is in between inflationary energy density and the energy density in radiation domination at some point. So to have the scenario you were thinking about where the bubble keeps expanding, you would have to have lower energy than the universe around it. Right, like if it's Mikowski or AES or something, that's a different story. But here, as Cami said, it's an overdensity. Once it enters the horizon, like any other overdensity, it will generically follow black hole.
A naive question. So how do you get the correct abundance of them? Like, because naively you think that when they form during inflation, they'll be diluted away like monopoles, and you wouldn't see any of them now.
Oh, dilute with
Inflation.
Yeah, so the thing that happens here is that since they expand like to horizon size, like basically right away they don't dilute with inflation because they're expanding with inflation.
You're saying one bubble collapses one black hole?
Yeah, doesn't that mean you get one per
one bubble
horizon?
per horizon?
Yeah, you get like, and in the end, like, it's only a small fraction of the Hubble volumes that actually have to go through this transition in order to get the correct abundance that we measure.
But it sounds like you're just getting one black hole
Yeah.
per horizon. So like I would only expect in one Hubble patch, I would only get one of these little hydrogen-sized black holes and not enough to account for the whole dark matter density.
Well, the Hubble patch during inflation, at the beginning of inflation, is different than the Hubble patch now.
So you're saying you'll get one per horizon post-inflation?
I'm saying that
Or
during inflation, like, you can only generate one per horizon, but nowadays, we would see more than one per horizon.
different from the model story? I guess
Yeah, how is it different from monopoles then?
we're confused because usually like you invoke inflation to say like, oh, you don't get so many monopoles per horizon because, you know, they're tied to inflation in this way, and so you only get one monopole per horizon, and so you don't have that many. Here it seems like you're trying to do the opposite, where you're trying to say, like, the horizon size is small when these form, and now the horizon size is so much bigger that you can have many of them. So I'm confused about how to reconcile these two things.
Well, what happens when the universe switches from inflation to radiation is that, I don't know the monopole story, but what happens
Usually
when,
for monopoles, you're assuming they pre-existed, and then or monopole inflates them away, so they're not around. She's making them during inflation,
I see.
so she gets to.
it's
keep
the
with
fact
them.
that it's during inflation that's making,
So there is the exponential creation rate of these things, right? And that's what dictates at the end what will be the balance.
Mhm.
They also get stretched, the monopoles don't get stretched, right? So
Yeah.
that's a big difference.
You're gonna do a calculation of the abundance probably, right?
What?
Are you gonna do a calculation of the abundance at some point?
Yeah, I can. Okay. So, yeah, for a black hole of our mass range, the horizon crosses at 10 to the minus 19 seconds, which is well within radiation domination. Okay, so now we're gonna want eventually to, in a minute, to try to understand the different times during inflation at which the bubble can nucleate, or how wide the spread can be of different nucleation times. But first, we're gonna have a little aside and ask what's going on inside of the bubbles of the black holes. So it turns out that if the bubble expands enough so that if it expands larger than its interior de Sitter horizon, the bubble actually inflates to a baby universe. And in our mass range, they do this. So I'm going to draw the Penrose diagram.
So you're assuming here that CC is positive inside, because also it could be collapsing universe inside. It's negative.
Yeah, it's positive.
So that's essentially
inside the bubble. Well, I mean, we know that it's higher than the radiation.
it is.
So okay, yeah. So this, by the way, it's not relevant to anything you would observe, because from our universe we would still just see this as a black hole. But it's kind of interesting to think that these little tiny hydrogen-sized black holes that are all over our universe have their own inflating universes inside that can also go through these transitions. So yeah, we just have these are the event horizons and the black hole, and this is R equals 0. And then the inflating bubble is connected to our own universe through a wormhole.
Sorry, Ken, what is the line that says FRW mean? Is it outside of that it's our universe?
This is FR, this here is like, this is like our universe.
Okay.
This stuff is kind of like, basically this line is supposed to denote the shock wave of the bubble. So like in between this stuff, it's like, it's not exactly FRW. But I don't think that's too important for understanding.
So the solid curved lines are not horizons, the dashed lines are horizons.
Yeah, these are horizons.
So there's like two different regions. One is like our universe in the standard model vacuum. There's
Yeah.
some other universe with some other that's maybe stable or not vacuum, and then in the middle it's not quite settled into a vacuum.
I think in the middle it's just that it's like experiencing the perturbations of the shock wave. Yes.
The inflating bubble region, is that an asymptotic future infinity? It's like the center and it just keeps growing?
Yeah, I
Okay,
think so.
okay, follow up. This black hole, it's evaporating in sort of on both sides. Some Hawking radiation is going to the inflating bubble region, and some Hawking radiation is in our region. So from our perspective, it looks like there's information loss? Because we don't get all the information that fell into this black hole.
Sorry, why? Why is that from our side that we see that? They're having.
Because, so let's say the initial state of the universe is a pure state. Some of that information is going to get stuck in that inflating bubble region, let's say. So from our perspective, the state is going to be some density, some mixed density matrix.
Would it not just be inaccessible to us?
Right, can anything stay in that inflating bubble indefinitely? How would we lose anything?
Actually, I think I know the answer to my question.
Maybe you can
tell us.
That's why you have a professor.
Okay, then you have, okay. So essentially what's gonna happen is that the entire interior, including the inflating bubble, is going to be in some funny way encoded in all the Hawking radiation that's in our universe.
But also this diagram doesn't show evaporation part, right? So evaporation, it will be like.
The operation?
Well, this diagram doesn't include Hawking evaporation yet, right?
Oh, sure.
Yeah, there should be, yeah.
So you think there should be some way to tell if the inside is inflating or not?
Theoretically.
You just have to measure the Hawking radiation.
Yeah, I'm not sure the telescope technology is there yet.
Okay. That's all I really have to say about that.
It just reminds us that if we ever do observe Hawking radiation, we should observe the living crap out of it.
Okay. Now I'm gonna so now since we have that the mass equation is exponentially dependent on the nucleation time, we want to kind of study what the spread of the nucleation time is. And in order to do that, we have to understand the tunneling a bit better. So during inflation, we're assuming that we have two scalar fields. And they're gonna have a potential that looks like this. There's a valley in the phi direction, and it's separated from a lake. And there's a barrier here. So we start off with a wave functional that's in the valley, and rolling down the valley, it's a slightly sloped valley, so it just corresponds to slow roll inflation. And classically, there's no way for the wave functional to get over the barrier and into the lake, but quantum mechanically, there's a chance that it could tunnel from the valley to the lake, and tunneling from the valley to the lake corresponds to the nucleation of the vacuum bubble. So I think, yeah.
What are phi and x?
They're just two scalar fields that we have during inflation. This is their potential.
Oh, okay.
Okay. So the tunneling from the valley to the lake is mediated by a Coleman-DeLucia instanton. Usually, when we have an instanton, it's going from one minima to another, one minimum to another minimum. But in this case, we have a bit of a complication. So this is instanton. In this case, we have a complication because we're tunneling from a time-dependent initial state. And to our knowledge, this hasn't really been studied before. If the valley here were symmetric, then the instanton would just go directly from the center of the valley to the lake. It's not, the slow roll breaks the symmetry, but so this line would actually shift up a little bit. But we still expect that there's going to be one instanton. Which means that there's one point on the valley that is at the end of the trajectory from tunneling from the valley to the lake. So basically there's one point on here that you tunnel from. That doesn't mean that the tunneling only happens at one point automatically, at one time automatically, because it's quantum mechanics, so this is a wave functional, and it doesn't have a definite position. So we wanted to understand what the rate is for tunneling at different delta phi's, or we're going to call the distance from where we want to get the tunneling rate to the endpoint of the trajectory, delta phi. So we wanted to see how quickly the tunneling goes to 0 for non-zero delta phi's. So we did two approaches to this. One is a numerical estimate. And in this case, we deformed the potential. So at the point that we wanted to calculate the tunneling rate from, we add a little minimum into the potential, an infinitesimal minimum. And then we used a Mathematica package that calculates the instanton from the usual minimum to minimum. And we expect that this would be a good approximation because we can make the deformation arbitrarily small.
Sorry, where on that did you put the deformation?
Okay, so like, say we want to, if this is delta phi, like we want to estimate the tunneling from this point
to the lake.
Yeah, I mean, yes, we want to, yeah, exactly. So we put a tiny little, like, we know that in the actual picture the instanton trajectory is here, but like there should be some way of estimating what the tunneling is up here, and so we put a tiny little minimum there, and so then you can actually calculate the instanton just using like the numerical simulation, since you're actually going from a minimum to minimum, so it's not a time dependent initial state anymore. And then we do that for like we want to get the dependence on delta phi, so like we do that for little points all along there. So that was one estimate, and then another estimate was doing an analytic two-step process where first we calculate the fluctuation from the point delta phi to the point on the trajectory. So first we calculate the probability of it fluctuating from here to here, and then we just use the standard instanton trajectory from that point.
So Cami, like you're calculating some volumes in phase space given some initial configuration, and that is like how much barrier you have to tunnel through. That's the other sort of the calculation of the instanton what we would do. And what's the potential like? I mean, what's that drawing? Like, does it depend on the ratio of the masses of the scalars? How one couples to itself more or less? Is there any particular feature, in particular having two light fields, we should get that sort of plot to calculate the tunnel?
I don't actually remember what the form of the potential was, but it was just a quadratic.
You're asking how the instanton depends on the form of the potential?
Right, for example, yes, I mean,
It depends a lot on it, but as long as it qualitatively looks like this.
no, that's my question. So, but I mean, that's if qualitatively looking like this is a general feature of potentials. That's my question.
Potentials like that have
The
a
question.
local minimum.
Okay.
Sort of- yeah.
Okay, so yeah, for the analytic approximation, we first calculate the probability that it fluctuates and then that it tunnels. And for this, we get the full action by just adding up the sum of the action of each of the two steps. And then the tunneling rate is given by e to the minus b, where b is the difference from between the action of the instanton and the action for the wave function should just stay in the valley. So both of these approximations gave us the same dependence on phi, which is the probability of tunneling at a point delta phi is equal to minus c, where c is just a number, it's about 100. Delta phi squared, r squared. This is the radius of the bubble. Okay, so this probability is unsuppressed when delta phi is less than about 1 over CR, which is 1 over 10R. Then during slow roll, delta n, the spread in the e-folds, is related to delta phi by 2 pi power spectrum. This is a power spectrum of gauge invariant curvature perturbations. It's a small number times delta phi over h sub I. And then if we put in this inequality, we get that delta n is less than about pi over 5. So yeah, this is about 10 to the minus 4.5. And this number, we expect it to not be much less than 1. So we can get that delta n is much less than 1. And then we can relate this to the mass using the equation that we had before for the mass.
Sorry, why the number cannot be much larger? That small bubble, size was a bubble in Hubble units, right? At the time of
At the time of tunneling?
yeah. So in principle, it can be quite small.
It's I think for the models that we were considering, it was.
Well, it is model dependent, but
it could be, yeah, but it would have to be.
The point is, yeah, I guess the point is that it can be less. We can get a really like tight constraint on delta n in a natural way.
Your tunneling probability, does it depend on how tall your ridge is?
Yeah.
Where is that? Is it in the constant C? How do you fix that number?
Oh, the constant C we fix that by we fix that with the numerical approximation.
But that depends on your potential profile.
Yeah. This.
How do you fix your potential profile?
What? How do I fix my potential?
Yeah.
We just assume a specific
The slow roll part I understand, but how about the horizontal part? Like the one.
Well, I mean, we are basically coming up with this potential. Like it's not like it has to be a certain way. So we just come up with a potential that I mean, it's definitely theoretical where it's just like imagine that during inflation there's a potential of this kind, and then
I think he's asking about B. No, you didn't write the rate actually. You wrote the delta phi dependence, but not the full rate. You wrote P of delta phi, but there's also just the B. There's just the there's that.
Yeah, so sorry, what's the question?
What is B there?
B here is the difference between, this is the action of the instanton. And this is the action to stay in the valley.
So basically you just pick some B, you pick some B and then how do you fix B?
Well, B is fixed by the form of the potential.
And then you pick some potential. Okay.
It's not that you pick B first, it's that you calculate the action of the instanton, like, first you pick a potential, you pick a specific form of the potential. And so yeah, we picked a specific form, but the argument is that like the general consequences hold regardless of like the particular form, but just a potential that looks like this. Yeah, and then you can calculate the action of staying in the valley and calculate the action of the instanton using this approximation, and that's how you would get B in that case.
Can you remind what delta R is?
This is the power spectrum.
Ah.
Yeah. Okay, so now that we know that it's possible to get a value of delta n much less than 1, then we can relate the mass to the spread of mass to the spread of n. And this tells us that we can have delta m over m much less than 1. And this means that we can have a very monochromatic mass spectrum. So the key ingredients that went into getting the mass spectrum to be monochromatic is first the fact that this transition only happens. This transition peaks when the vacuum expectation value is right overlapping the edge of the trajectory, and it's highly suppressed for values away from that. And then also that the mass of the black holes depends only on the nucleation time, which is a product of the fact that it grows with inflation, so it's exponentially dependent on when it formed. Right, so that's all I have. Basically, in this mechanism, we show that it's possible that you can take a pretty natural form of potential and some assumptions of what happens during inflation, and you can get a monochromatic spectrum of teeny tiny black holes that could account for all the dark matter in the universe, and that each of them could have their own little baby universe inside of them.
So could you say again, I'm sorry if I missed this, but like what are the free parameters of this model? Like what did I need to tune, for instance, for me to get this delta or this m to be asteroid size?
So this m to be what?
I think, so you predict a very monochromatic spectrum. Right. If I say this is the model for dark matter, I would want that mass to be asteroid size. Or sorry, asteroid mass. So that it's 100% of dark matter. So what would I have to tune in this model?
Oh. Well, yeah. You mean to get the right amount of to get the right abundance?
Yeah.
You would tune like how many Hubble volumes this transition happens in. So the tunneling rate.
So it's essentially just you're tuning like the height of the barrier, right? Is that free parameter enough to?
I think so.
There's-
So that would depend on the coupling strength.
But there's also, yeah, there's like the mass of both of the fields.
Yeah, good.
Yeah.
Oh, I was just wondering, if there was any reason to believe that this potential is the potential that occurs during inflation, other than the fact that it gives you primordial black holes?
No, I don't think so. I think it's just that, like, I mean,
Is it like is it potentially generic? Like if you just had some rolling model of inflation, and you had a potential dip somewhere else, would you automatically expect to get primordial black holes, or is this a condition?
no, I think that, yeah, I think the argument is more general than just this particular form of the potential. As long as you have like some kind of vacuum decay, there's the potential to make them.
You can also get this from domain wall nucleation. It doesn't have to be vacuum bubbles. But how generic it is in the eye of the beholder. Unless you know what the measure is on the space of possible potential.
I mean, it's pretty generic, right? Like in whatever effective field theory describes the early universe, you'll have a range of potentials, and some of them will be higher and lower, and so some of them will tunnel into the other and be like varying degrees of semi-stable. So like I think the general phenomenon that Kerry drew there is like pretty general, right? You have a landscape of potentials.
Mm-hmm.
I mean, if there is a landscape of potentials, then maybe the selection effect that leaves us in this universe is that potential produces the standard model early enough to make all these other things collapse. Because presumably there are as many inflation states as there are string vacuums. Right? Don't we expect there to be 10 to the 500, or maybe only half of them are inflation states?
Sure. If it's greater than 0 or not, but
Yeah. Okay, thank you very much.
Oh,